Alright, so the side-splitting theorem. Side-splitting theorem states that a line parallel to one side of a triangle divides the other two sides proportionally. So what that means in the context of this triangle down here is that means that if I have a line drawn inside the triangle that's parallel to one of the sides, so that's what these little arrows mean. That means that these two lines are parallel. And according to this theorem, if those lines are parallel, it's splitting the triangle into proportional parts. So proportion means two ratios are equal. And the way this helps us is if I am trying to find missing measurements, I can use these ratios, these proportional relationships, to solve for missing measures. So the question is, well, what would be a correct proportion to create using this figure? And the name of the game is corresponding parts. So A corresponds to B because they're on the same side together. And A corresponds to C because they are both the two upper segments created by this parallel line. So that means I can write two different proportions that would be true. I can say A to B because they're corresponding, and that would equal, and A also corresponds to C. So if A's on top here, C goes on top there. So C to D. This would be a true proportion because everything corresponds. The two that are in a ratio together and the two that are across from each other. Another way to write a proportion that would be true based on this theorem is to go across the figure. So instead of A to B, I could say A to C. So A to C equals, and then again, remember corresponding parts. A corresponds with B, so B has to go on top, and then D. So these would be two proportions that would be true according to this theorem. Well, how do I apply this? Well, if I get a problem that looks like this, which is pretty much just like our example, and I'm told that these two lines are parallel. So either they'll give me that information in the directions or they'll be marked with the arrows. So if they tell me that, or if it's given in the figure, that means I just set up my proportion using the system I just showed you. So I could say 10 to 5 equals x to 4. Or I could have also put 10 to x, 5 to 4. Either would be correct. Either would give me the same answer. Cross multiply. And then divide. And we find that x equals 8, so the missing measurement is 8. Now, that's a pretty straightforward example. What happens when we no longer just have the side measurements, but now we have the measurements of the parallel lines? Okay, that changes my relationship completely. It kind of switches from the side-splitting theorem to two parallel lines creating similar triangles. So this 10 is a measurement of this segment here. Well, that segment corresponds to this segment and to 5. I don't have this segment measure. So even though it's true to write 5 to 10, it would not be true to write x to 18 because 10 doesn't correspond to 18. It corresponds to this segment. So this would be considered the incorrect way to set up this problem. What I want to do instead is think little triangle, big triangle. So my little triangle is this small one here created by the parallel line, and my big triangle is this larger one here. So my first ratio could still be 5 to x, but instead of writing 10 to 18, you have to think little triangle, big triangle. So in the little triangle, the length of this side was 5, but in the big triangle, the length of this side isn't 10, it's 15. So instead of writing 10, I write 15 to 18. And then I cross multiply and solve. So this would be 90 equals 15x divided by 15, and x equals 6. So those are two application problems of the side-splitting theorem. I hope this made sense.